what if I want to get the mass of molecules? Okay, so to get the mass of molecules is pretty easy. You're going to take your periodic table and use the average atomic masses. So if you look on your periodic table and you find nitrogen, nitrogen's average atomic mass is 14.01. Find nitrogen down at the bottom. But I have two nitrogens in molecular nitrogen, so I'm going to have to multiply that by 2. And again, with sig figs, okay, just take these to the 100th place. Average atomic masses should always go to the 100th place. That's going to be 28.02. And then eventually the units are going to be grams per mole. You don't know what a mole is yet. That's going to change in about 10 minutes, right? If we look at the next one here, if we want to get the average atomic mass of glucose, C6H12O6, what we do is we're going to take the number of carbons, which is 6, and we're going to multiply that by the average atomic mass of carbon, 12.01. Then we're going to take the number of hydrogens, 12, and we're going to multiply that by the number of, or the average atomic mass of oxygen, which is, or hydrogen, which is 1.01. And then we'll add to that the number of oxygens, which is 6, times its average atomic mass rounded to the 100th place, which is 16.00. So if you pop that in your calculator, 6 times 12.01 plus 12 times 1.01 plus 6 times 16, that will give you, let's see, I think it's 180.18, but hang on. 180.18, and then that's going to be, again, grams per mole, but we'll worry about those units later. Right now, you're just getting the mass of these molecules. What you're saying is if carbon on average weighs 12.01 and you got 6 of them, we can just kind of add this together. Now, you do have to watch out for parentheses, right? Let's get the average atomic mass of calcium nitrate. So if we do this, calcium weighing in at 40.08. You got 2 nitrogens. See that 2 gets distributed in, right? Uh-oh. Oh, no. Can I edit this? I don't think I can edit this. Oh, yes, I can. I got it figured out. Fantastic. So now I got 2 nitrogen. That 2 gets distributed. So it's going to be 2 times nitrogen's average atomic mass, which is 14.01, plus the average atomic mass of oxygen, which is 16 times 6. You got to multiply. 2 times 3 is 6. You get 6 oxygen. 6 times 16. Okay, and then we can get an average mass of that molecule, 40.08 plus 2 times 14.01 plus 6 times 16, 164.10. And then again, that's going to be grams per mole. So does everybody see how to get the average mass of a molecule? It's kind of, you just take the average atomic masses and you multiply them together. There's a giant fly in here. Oh my goodness, it's huge. Any questions on that? Okay. Percent composition is kind of an easy thing. So this allows you to determine the percent of a molecule's mass that comes from each element. It's pretty easy. The first thing you'll do is you get the average atomic mass like we were doing. And then you'll take the individual mass of each element divided by the total average atomic mass, multiplied by 100, and you can get the percent composition. Lots of words for a simple thing. Let me walk you through it. Let's say I want to figure out the percent by mass, the percent composition of carbon in this hydrocarbon. This is butane. This is the fuel that you would find in a lighter, like a Bic lighter or something. So we want to get the percent carbon in here. The first thing we have to do is get the total average atomic mass. So take a look at your periodic table. The total mass of C4H10 is going to be 4 times the average mass of carbon, 12.01, plus 10 times the average mass of hydrogen, 1.01. And that's going to give us the total, oh my gosh, it's going to give us the total mass of butane. So 4 times 12.01 plus 10 times 1.01. That's going to be an average molecular weight of butane. That's 58.14 grams per mole. Now, if I want the percent that's coming from just the carbons, what I have to do is take the mass from just the carbons. So the mass of just the carbons, this is the carbon mass. That's going to be 4 times that 12.01. That's going to be, what is that, 48.04, right? 48.04. And now what I can do is I can get the percent of the total mass that comes from the carbon. Take the mass from the carbon, divided by the total mass, multiplied by 100, and you'll be there. So it's going to be 48.04 divided by 58.14. And then to make it a percent, you just multiply by 100. So if we do that, 48.04 divided by 58.14, that's going to be times 100. That's going to be 82.6. Again, I don't care about sig figs when it comes to percents. 82.6% by mass from the carbon. The hydrogen you could obviously get by just doing 100 minus that, right? And that would tell you because there's only 2 things in that compound. All right, let's turn you loose. Here's what I'd like. I'd like the percent mass of oxygen in magnesium nitrate. Go ahead and see if you can get that one right. All right, so you want to get the total mass of magnesium nitrate. So that's going to be 24.31 plus 2 times 14.01 plus 6 times 16. That's a total mass of 148.33. And again, I can punch a number in wrong. So if you see a mistake I made, please just yell at me. And then I need to get the mass of 6 oxygens. So it's going to be 6 times 16. So the mass from just the oxygens is 96. So I'm going to take 96 divided by 148.33 times 100. So 64.7% of the mass is from the oxygen atoms in magnesium nitrate. How do we do with that? Two thumbs up. So I'm talking about 2 people got that right. 3 people, even better, 4 people. All right.
I have a question.
Yeah, what's up?
So for the total mass, I got 148.31. Does that really does that small?
No, it's fine.
make a
Yeah, I mean, I round everything to the hundredths place. So if you want to get what I got, round everything to the hundredths place correctly, right? So actually, you know what? Is magnesium 24.32? I'm just trying to
24.305.
Oh no, so it's 24.31. So anyway, yeah, 24.31, 2 times 14.01, 6 times the oxygen on the periodic table is 15.999. So I rounded to 16.00. So, but no, to answer your question, no, man. I mean, if you had 148.31, close enough. You know, I'll take it. It'll be fine. Okay. Cool. Oh boy. 811. Perfect. Those of you who have taken high school chemistry in the past, you may have some trauma here as well with the mole. I'm going to try and break it down for you, make it a little easier than maybe you got it in high school. The mole conceptually is no different than a dozen. So what is a dozen? Well, a dozen is just 12 of something. right? I mean, you can have a dozen pencils, you can have a dozen eggs, you can have a dozen shirts, you have a dozen cups, whatever, right? It just means 12 of something. The mole is exactly like that. Just instead of 12 of something, it's just a wee bit bigger. Okay, a mole is 6.022 times 10 to the 23rd of something. So this number is ridiculous. Okay, that is a 6 with 23 things after it. Okay, I will write it out one time just so you can like put in perspective how big this number is. So a mole is defined as 6.022 times 10 to the 23rd of something. So that's a 6, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, right? Good thing I didn't buy the smaller whiteboard when we got shut down in the spring of 2020. Friday the 13th. Okay, this is a mole. Now that is maybe the biggest number that you have ever had to look at. It is kind of silly. Okay, I will try and put this number in perspective for you. If you had a mole of sheets of paper, so if you had 6.022 times 10 to the 23rd sheets of paper, and you stack them on top of each other, it would go from here to the moon. So it would go to the moon and back 13 and a half times. It would make it to the moon 13 times, and it would come back. It would be halfway back once, so it would go from here to the moon 13 times, and then it would go to the moon once. That's crazy. Sheets of paper is not very thick. But if you had that many sheets of paper, it would go to the moon like 13 and a half times. That's pretty nuts. Okay, if you had a mole of seconds, if you had 6.022 times 10 to the 23rd seconds, you would that would be equal to 4 million times the age of the Earth. So we think the Earth is, I don't want to make up numbers here for you. I feel like I have it on another slide. Yeah, so we think the Earth is about 4.5 billion years old. That's what I was going to say. So if you went from the moment that the Earth was just forming as a molten rock, okay, and gases collecting out there in the planetary nebulas and whatnot, if you went from that to now, 4 million times, you would spend your mole of seconds. If you had a mole of marbles, I like this one. If you had a mole of marbles, not the shooters, the little guys, that would cover the entire planet 50 miles deep in marbles. Like, if you put saran wrap over the ocean, the whole planet would be 50 miles deep in marbles if you had a mole of marbles. So that's pretty insane. Like it's hard to wrap your mind around a number this big. It's like in your mind, it's almost infinity, right? Why on earth would chemists need a number this big? We need a number this big because this is how many atoms are in just 12 grams of carbon-12. Easy to remember, right? Because it's 12 grams of the isotope carbon-12. It's just 12s, right? Carbon, most stable elemental form at 1 atmosphere pressure, is graphite. Imagine having 12 grams of graphite in your hand. It would be a little mound of graphite, right? You could hold it easily in the palm of your hand. Okay, it'd be a little mound of graphite sitting here. In that mound of graphite in your hand, there would be that many carbon atoms. If you're writing with a pencil right now, and you make a period, just a normal period with a pencil, because pencil contains graphite. If you make a period on a piece of paper, the average size period on a piece of paper is about a billion-ish carbon atoms. That's how many carbons you leave behind on the paper. It's about 1 billion in that carbon. That's insane. Okay, moral of the story, atoms are really tiny. So when we're talking about atoms or molecules, which are made of atoms, we need this ridiculous number. Okay, it is named in honor of somebody. It's named after Amedeo Avogadro. He is the strapping gentleman that was on this previous slide. Here is an Italian scientist. Come on. Probably second only in fame to Galileo. I don't know. No, I'm sure there's other wonderful Italian scientists, but Amedeo Avogadro right up there near the top. Okay, and he's the dude who, he figures out this kind of mole theory. He doesn't necessarily come up with this 6.022 times 10 to the 23rd thing, but he comes up with this idea of the mole, and then they named it after him, or they honored him with it. So a mole is just, 6.022 times 10 to the 23rd of something. And we are going to do some dimensional analysis with the mole. Okay, but before we do that, we need to do some dimensional analysis with a dozen. Because listen, a mole is no different than a dozen conceptually. Okay, so if you can do conversions with a dozen, you can do conversions with the mole. So let's try this out. You are going to think I'm totally nuts, but I've been doing this 13 years and I have no problem with students understanding the moles. So just hang in there with me and do it along with me, and it's all going to work out. You're going to be okay. Let's see. I don't know. My father he's retired, was a poultry farmer, and ran his own poultry business into the 80s, and then automation, as everything put them out. They just hand gathered the eggs. Never gonna work. So he went to work for Kreider's, in Mannheim, one of the big, automated things. Chicken houses now cost over $1 million. I don't know what farmer has $1 million to put out there, but I digress. Family farming over, except for the organic niche stuff. That's, you can survive. But anyway, let's say you're hand gathering eggs, back in the 1980s. And you gathered 14,750 eggs today. And you want to know how many dozen eggs did you just gather? Every person in this class can pick up a calculator and get me an answer right now. That's great. That's because you have an IQ above, 80. I don't care about the answer. What I care about is the method. We're going to use dimensional analysis to get there. And we're going to treat a dozen just like a conversion factor. Okay, that we were doing before when we were doing the inches and all that stuff, right? I'm telling you, yes. Do I really care if you can tell me how many dozen eggs this is? No, I do not. What I do care about is, can you do the dimensional analysis process with this? So just kind of play along here. All right. We're going to use the conversion factor that there are 12 eggs in a dozen. And we're going to set this up just like dimensional analysis, where we're going to take what you're given, 14,750 eggs. We're going to put it over 1. And the whole point, again, this is what we did in all those conversions, right? You take what you're given with a unit. In this case, my unit is eggs, and you put it over 1. And now the whole point of dimensional analysis is going to be to get eggs to cancel out, right? That's how it works. So it takes the guessing out of, where do I put this? 12 eggs is going to go on the bottom. And then the 1 dozen has nowhere to go but the top. And you can see what we all knew ahead of time. You need to take 14,750 and divide it by 12. So we're going to do that. Now, you get into an ethical, or not an ethical, but you get into a sig fig kind of philosophical, is the word I'm looking for, discussion here. You probably determined this by counting, right? Like you counted the eggs, which means it's not actually a measurement. It's actually a qualitative observation, not a quantitative observation. But anyway, let's pretend that it's 4 sig figs, trailing 0, no decimal point. So I want 4 sig figs here. You just hand gathered 1,229 dozen eggs. There for a while, a dozen eggs was like 99 cents, which is sickening how cheap that is. A dozen eggs, $1. Anyway, I think it's more than that now, obviously, but till you feed the birds and you pay for the electric, and it's like, is it the winter? But it's like how do you make any money? Anyway, there's that. Let's go the other way now. So we can, with any conversion factor, go in either direction. Let's say that, I don't know, the day before you gathered 1,582 dozen eggs. How many eggs did you pick up? Go ahead. I want you to try to do that. Again, my son is 6. He could, if I handed him a calculator, he could probably do that. Okay. I don't care, but what he could not do is the dimensional analysis. I want to see the dimensional analysis. Okay. See if you can you set that conversion up right? All right. 1,582 dozen over 1. This time we need the dozen to cancel out. So the 1 dozen going to go in the bottom, and 12 eggs going to go on top. So 1,582 times 12. You gathered 18,984 eggs. But if we get all sig figgy, 4 sig figs, 18,980 eggs. Listen, if you're sitting at home and you're saying this is a joke, good. Because the mole is no different than this. Instead of being 1 dozen is 12, we're going to have 1 mole is 6.022 times 10 to the 23rd. And if you can do this, you can do the mole, right? Everybody can do the mole. Okay. I've taught the mole to all kinds of people. All right. But if you just blow off the dimensional analysis, then you can't do the mole. So let's try some mole conversions. One mole, and yes, we chemists are so lazy that we chop the E off of mole. That is lazy. All right. Chemistry is hard. It's all right. You burn out real fast. Okay. So we cut the corners where we can. We do not put the E on mole. Awesome. Anyway, 1 mole is 6.022 times 10 to the 23rd of something. Now, if you are talking about having anywhere near a mole of something, that something has to be small, which means it's going to be either an atom or a molecule. Atoms or molecules. Those are typically the units, right? Where we had 1 dozen, 12 eggs, or 12 pairs of pants, or 12 shirts, or 12 red. I mean, when you're talking about the mole, it's almost always atoms or molecules that you have 6.022 times 10 to the 23rd of. Okay, so if it's an individual thing, then we use the word atom. And if it's more than 1 atom, we use the word molecule. So let's do, we'll do a couple. Let's say that you have 1.95 times 10 to the, 22nd atoms of gold. You're rich. And I want to know how many moles that is. Here's how we set this up. You take what I give you with the units, and you put it over 1. 1.95 times 10 to the 22nd atoms of gold. We're going to put it over 1. And then we need atoms to cancel out. So dimensional analysis takes the guessing out of that. So how are we going to get atoms to cancel out? Well, 1 mole doesn't go in on here because it's not going to cancel out. Avogadro's number, 6.022 times 10 to the 23rd, that has atoms in it. Again, we're using the word atom this time because that's an individual atom. So we're not using the word molecules this time. So 6.022 times 10 to the 23rd atoms of gold. That's what's in 1 mole of gold. And now this is where you're going to use that beautiful E button. Talked about the E button last time. This is what, or when we were in class, right? And I walked around and showed everybody their E button. If you're rocking a graphing calculator, that's a Texas Instrument, it's second comma. Okay, big fan of the E button. Okay, if you're not getting it right, let me know. Okay, so I'm going to use the E button when I put this in. I'm going to take 1.95 E22, 1.95 E22. Again, the E takes the place of the times, the 10, and the caret. No times, no 10, no caret, E. 1.95 E22 divided by 6.022 E23. And if you do that correctly, your calculator should say 0.0323812.687. If you do not see 0.0323812.687 on your screen, you do not know how to use your E button correctly. You need to let me know. Sig figs, I got 3 sig figs here. That is a leading zero. So with 3 sig figs, it's going to be 0.0324 moles of gold. If you owned 1.95 times 10 to the 22nd atoms of gold, you would own 0.0324 moles of gold. You're not that rich. I mean, you got some money. Not a whole lot. That's like the first kind of way. Let's go the other direction now. Let's say you had 17.0 moles of carbon dioxide, and I want to know how many molecules that is. So how many molecules are in 17.0 moles of carbon dioxide? So we're going to do the same thing again, where this is a conversion, and this is our conversion factor, right? So we're going to take what we're given, 17.0 moles, put it over 1. This time I need moles to cancel out. So if I need moles to cancel out, the 1 mole goes on the bottom. And Avogadro's number, 6.022 times 10 to the 23rd, goes on top. And this time I'm going to multiply. So 17.0 times 6.022 E20. 17.0 times 6.022 times 10 to the 23rd, you're going to get 1.02 times 10 to the 25th. If you look on your calculator screen on the far right side, it should say E25. People overlook that all the time, but that E25 means times 10 to the 25th. So you have 1.02 times 10 to the 25th molecules of CO2. When you do conversions with the mole, you are doing a topic in chemistry called stoichiometry. Okay, now this gets incredibly complicated, but this is like the foundation of how we do these things. Okay, the true unit, SI unit for amount, is the mole. People misuse mass and amount all the time. But because different atoms have different masses, we can't compare things unless we standardize that. And our standard is the mole. Okay, so really we have to be in moles before we can compare 2 different substances. We can't, let's try and say, mass is not amount. If I said picture 20 pounds of apples, you'd picture like a bushel. It's a whole bunch of apples, right? I don't know, 30 apples, whatever. If I said picture 20 pounds of watermelons, okay, that would be like what, 2, 3 watermelons? Okay, you have 20 mass, 20 pounds, that is not amount, right? Amount is like counting the individual things. And the mole is like counting. It's like saying 6.02 times 10 to the 23rd of the things. We have to be in moles when we compare things. Now we can go from mass to moles. That's actually what these average atomic masses do. So the average atomic masses on the periodic table, I said earlier, these have units of grams per mole. Grams per mole. What these average atomic masses actually tell you is how much a mole of that substance weighs. So what it's saying is on average, 1 mole of copper, if you wanted to have 6.022 times 10 to the 23rd moles of copper, it would weigh 63.55 grams. These average atomic masses are actually our bridge between grams and moles. So you have to remember that these have units of grams per mole. And these are going to allow us to go from mass to moles because all these elements have different masses. It's going to allow us to go back and forth. So let's try some of those using dimensional analysis. So let's stick with copper. Why not? Let's say you have, I don't know, 2.15 moles of copper. And I want to know what would that weigh in grams. Well, that's where you're going to have to go to the periodic table, and you're going to have to find that molar mass or atomic mass of copper, and it's 63.55. So that mass from the periodic table for copper is 63.55. There are no units written there, but the units are grams per mole. It's going to be really important. Grams per mole. We're going to set this problem up just like dimensional analysis. So 2.15 moles of copper over 1. And now again, our whole point is to get units to cancel out. So this is going to take the guessing out of do I multiply by 63.55 or divide by 63.55. Here's how this works. We're going to have to multiply. Here's why. If I multiply by 63.55 grams of copper per 1 mole, you can see that the moles will cancel out, right? Remember, it's grams per 1 mole. So in this case, if I'm going from moles to grams, I would want to multiply by the molar mass. If I divide it by the molar mass, it won't work. Look, if I put the 63.55 grams on the bottom and the 1 mole on the top, that doesn't cancel out. Okay, so the mass goes on the top, and the 1 mole goes on the bottom. So if you want to go from moles to grams, you're going to multiply by the molar mass. So 2.15 times 63.55. If you had 2.15 moles of copper, that would weigh 136 grams. Now we can also go the other way. We can take a mass and convert that to moles. Let's try that. Let's try this one for a molecule. Let's say you had 45.2 grams of rust, Fe2O3, iron 3 oxide. And I wanted to know how many moles that was. Again, you always take what you're given with the unit, put it over 1. So 45.2 grams of Fe2O3, put it over 1. And now I need grams to cancel out. I want to end up in moles. That is the job of molar mass. But now you have a compound. So we're going to have to get the molar mass of this compound. So you're going to have to go to your periodic table. And this is the only time you will ever hear me say this. I do not want you to show the work. I want you to be able to just pick up a calculator, look at the periodic table, and add up that molar mass without writing anything down. Why? The answer, you're not going to have enough room. Like on a test or a worksheet or something, if you have to show the work for adding up that molar mass, you're not going to have room to do the problem. So this is where I'd like you to be able to grab a calculator, go to a periodic table. You can do it with me now. You got to find iron. Iron is 55.85. So we're going to do 2 times 55.85 plus, and then find oxygen, 16.00. You got 3 of them, so plus 3 times 16.00. Iron 3 oxide, rust, has an average atomic mass of 159.0 grams per mole. And now, dimensional analysis takes the guessing out of, do I multiply by 159.7 or do I divide by 159.7? Here's what it takes the guessing out of that. I need grams to cancel out, right? So I'm going to have to put that 159.70 grams on the bottom. That's grams per 1 mole. 1 mole is in the denominator of a denominator. It gets kicked to the numerator. So 45.2 divided by 159.7, that's going to be 0.283 moles of Fe2O3. What I have now given you is really two, what I like to say, tools for your chemistry toolbox. I had a trigonometry teacher in high school who we were going over logarithms, and I remember raising my hand and saying, "Mr. Brent, I mean, I can do this, but like I don't really understand what a logarithm is. Like, what is a logarithm?" And he said, "It's just a tool for your mathematical toolbox." And I was like, "Well, okay, but like, what is it?" And he said, "It's just another tool for your mathematical toolbox." And it was at that moment that I realized he did not know what a logarithm was. So in honor of him, I always describe this as saying you now have two tools for your chemistry toolbox. Your tools for your chemistry toolbox are this. 1 mole is 6.022 times 10 to the 23rd of something, atoms or molecules. You could also have a mole of electrons or a mole of photons or something, but for Stoich, it's atoms or molecules. And then you have the molar masses, grams per mole, so some molar mass. That's it. The only tools I've given you so far for your chemistry toolbox are you can go from moles to atoms or molecules, or you can go from atoms or molecules to moles, and you can go from grams to moles or moles to grams. Now, if you're smart enough, okay, you're probably realizing, wait a minute, couldn't we use these two tools one after another and make a two-step problem? And the answer is absolutely. Let's take a look. So, oh man, I don't know. Let's do gold again. Let's say your great 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 grandmother has just had a gold ring or something, and she's passed it down through the family or whatever. And you need some money. You got to hawk that thing, right? Okay, and before you hawk it, you wonder. I wonder how many atoms of gold are in this ring that was on my great 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 grandmother's finger and passed on through the generations. So you weigh the ring, and you find out that the ring weighs, I don't know, maybe 23.5 grams of gold. And we want to figure out how many atoms are making up that ring. How many atoms of gold are congealed together to add up to 23.5 grams. So the first thing we want to do in any one of these problems is to take the number and the unit, 23.5 in grams, and put that over 1. So 23.5 grams of gold over 1. If you do that, as always, I will give you a point just for getting the problem started. Because what I've found over the years is people just leave them blank. And if they have some incentive to just get it started, then they end up being able to do the whole problem. So I've always said for 13 years now, if you just do this, take what I give you and the unit, put over 1, I'll give you a point. Because most people can then get more points. It's just, anyway. I need to get rid of grams. The problem is, if we look in our chemistry toolbox, we do not have a conversion to get from grams to atoms. We have a conversion to get from grams to moles. But if you're a thinker, if I can go from grams to moles, then I can go from moles to atoms. It's just going to be a two-step process. So you need to find gold. And you need to get the average atomic mass of gold. So gold is the 79th element on the periodic table. And if you're finding it, I believe its mass is 196.97 grams per mole. Let's pull that up. It's 8:41 at night. The chances of me remembering that are not great. 196.97. Look at that. You teach chemistry, you can memorize a bunch of useless stuff too. Okay, so I need grams to go away. The beautiful thing about dimensional analysis is it takes the guessing out of it. The 196.97 grams has to go on the bottom, and then the 1 mole has to go on the top. Just like in dimensional analysis, don't touch your calculator yet, right? You're not done. I want to get to atoms. I'm only in moles. We got another step. Now that we're in moles, now we can use Avogadro's number. I need moles to cancel out. So 1 mole is going to go on the bottom, And Avogadro's number, 6.022 times 10 to the 23rd, and since gold is just an atom, we use the word atom, goes on the top. And now you can grab your calculator and you can just kind of, work your way through it. So this is going to be 23.5 divided by 196.97 times 6.022 E23. And your calculator should tell you the great grandmother's ring that you're about to hawk has 7.18 times 10 to the 22nd atoms of gold in it. There you go. 366. 366. So you can see dimensional analysis has guided us through this process, right? Where we just worry about getting units to cancel out every time, and you will be able to get it. It like essentially just takes the thinking out of doing these problems, right? It's all about using what you got, either molar masses or Avogadro's number, and getting the units to cancel out. Let's go in the opposite direction, and then maybe we'll call it a night. Oh man, let's see. A water bottle is 500. The average water bottles, the plastic water bottles, they're 500 milliliter bottles. Water has a density of 1. So in a water bottle, you would have 500 grams of water. Maybe you're super dehydrated, so you wonder, man, if I drink that whole bottle of water, how many molecules of water did I just put in my stomach? Dimensional analysis is going to help us do that. So how many molecules of water are in a 500 milliliter water bottle? And again, water has a density of 1 gram per mil, so it's 500 grams. Let's do it. 500 grams of water over 1. I need to get rid of grams. So is that the job of Avogadro's number or molar mass? Well, it's going to be the job of molar mass, right? It's the only one that's got grams in it. So we need to get the molar mass of water. This is the only time I'll say I would prefer if you don't show the work. So I want you to grab a periodic table and I want you to add up the average molar mass of water. So 2 times 1.01 plus 16. Water has an average atomic mass of 18.02 grams per mole. Dimensional analysis takes the guessing out of doing this, right? So I need grams to go away. 18.02 grams on the bottom. 1 mole of water on the top. Now I'm in moles. I'm going to get to molecules. That's what Avogadro's number does. 1 mole of water. 6.022 times 10 to the 23rd molecules of water. So a water bottle, which contains 500 grams of water, contains, it's mind-blowing, bottle of water, plastic bottle of water, there's about 1.67 times 10 to the 25th molecules of water in there. That's crazy. Absolutely crazy. This problem actually is in the same kind of direction, I realized. So maybe let's do one that goes the opposite way. I promise. Maybe about 2 minutes, and then we'll get you out of here. Questions on this? I'm going to go the other way. I want to do, I don't know. Let's say you want to know, you have an experiment that calls for 3.0 times 10 to the 22nd atoms of iron. And I want to know how many grams that is. So 3.0 times 10 to the 22nd atoms of iron, what would that weigh in grams? There we go. 3.0 times 10 to the 22nd atoms of iron over 1. I need atoms to cancel out. So we look in our chemistry toolbox. Molar mass is not going to help us. It doesn't have atoms, right? Okay, but Avogadro's number will help us. And Avogadro's number actually is the thing with the atoms. So Avogadro's number is going on the bottom. 6.022 times 10 to the 23rd atoms of iron on the bottom, 1 mole on the top. And now that we're in moles of iron, now we can turn that into grams using the average atomic mass. So if you find iron, iron is weighing in at 55.85 grams per mole. In order to get moles to cancel out, we want to multiply by that molar mass. 55.85 grams of iron on the top, 1 mole of iron on the bottom. So 3E22 divided by 6.022 E23 times 55.85. 2 sig figs this time. That would be 2.8 grams of iron. If a reaction called for 3 times 10 to the 22nd atoms of iron, you would need 2.8 grams of iron. You'd have to go to the balance and weigh that out.